Welcome to the Deep Dive, and thank you for trusting us with this stack of sources on object-oriented programming, or, OOP. This is one of those subjects that sits right at the intersection of computer science theory and just modern practical engineering.
It really does.
And frankly, it can feel like a really heady lift if you're trying to figure out which definitions matter the most.
It absolutely can. The sources you provided are excellent, though. They act almost like a technical manifesto for the approach itself.
So what's our mission today?
Our mission is to cut through the noise, to demystify these core concepts. Classes, objects, the famous 4 pillars. So you understand not just the definitions, but the why.
Right. Why did this paradigm take over modern software design?
Exactly.
That's right. Our goal is to give you the mental model that allows you to assess any large code base and do it quickly. You should walk away knowing exactly how these pieces of structure, well, fit together.
Yeah.
Okay, let's unpack this.
We have to start at the beginning, I think, with the foundational concepts of the entire paradigm.
Classes and objects.
Classes and objects. The sources define OOP as a programming approach that uses, quote, objects to design software. So naturally, the first question is, what's the relationship between the object and the thing that builds it?
Exactly. And I think the sources provide a beautifully clean metaphor here. A class is the blueprint. It defines the potential, the structure, and all the capabilities.
And if the class is the blueprint, the object is the operational instance created from that blueprint.
Okay.
Think of it like a cookie cutter and a cookie. The cutter is the class. It defines the shape, the ingredients, and every single cookie you stamp out is an individual object.
And they all share the same definition, but they have their own unique existence.
Precisely.
That distinction, blueprint versus instance, it feels crucial because the notes really emphasize the strict, ordered nature of OOP.
They do.
You can't stamp out a cookie until you've defined the cutter.
Exactly. The class must be defined before it can be used to create any objects. And that structural requirement, it shows you that OOP is an inherently top-down approach to organization.
It forces developers to think about structure and definition first.
Which is a massive win when you're dealing with complexity.
So let's open up that blueprint then. If a class defined everything, what ingredients are we bundling together inside it?
Okay, so when you define a class, you are essentially defining 2 complementary things. The data it holds and the actions it can perform.
Right.
The sources call these attributes, which are the data members, and methods, which are basically the functions or operations.
This sounds straightforward, but this bundling act immediately introduces the first, and I would argue the most fundamental pillar of OOP.
Encapsulation.
Encapsulation.
It does. And encapsulation is more than just, throwing data and functions into the same file. It's the principle of making a clean, self-contained unit where everything that defines the object lives inside the class definition.
Okay, but here's the challenge, right? This is often a source of confusion for learners.
Yeah.
Why is this better than just having, say, a struct with a bunch of related functions?
Right.
Isn't encapsulation just fancy organizational neatness?
That's a fair question. But if we look at the core intent, it's really about control. Encapsulation is about protecting the data.
Protecting it how?
By forcing external code to interact with the object's internal attributes only through its controlled methods. That way, you manage the integrity of that data.
That's the key insight.
Yeah, imagine a tightly sealed engine in a modern car. Encapsulation is that seal.
Okay.
You can start the engine, that's a method, or check the oil level, another method. But you cannot just reach in and arbitrarily change the pressure in one of the cylinders. That restriction prevents unpredictable behavior.
And that, I think, is the true payoff that's mentioned in the notes.
Yeah.
Creating readable and maintainable code. If something goes wrong with an object's data, you know exactly which methods, which entry points could have possibly altered it.
You don't have to hunt through the entire program.
Right.
It creates accountability in your code structure. It makes debugging manageable, which is just invaluable in software development.
Okay, so we've covered the fundamental building blocks, class, object, and the power of encapsulation.
Right.
Here's where it gets really interesting, because we move from organizing a single piece to organizing thousands of interconnected pieces.
This is where we get into the other pillars.
We need to look at the remaining 3 major concepts that elevate OOP from, like you said, organizational neatness to flexible, scalable system design.
And if we connect this to the bigger picture, these concepts, inheritance, polymorphism, and abstraction, are the tools that allow a small team to manage a system with millions of lines of code. They are all about managing complexity through relationships.
Let's start with inheritance. Definitionally, it's pretty simple. allowing one class to derive properties and methods from another.
But the impact is massive. Inheritance is often mischaracterized as just being about code reuse.
Oh, right, just saving time.
Exactly. But it's so much more powerful than that. It ensures systemic consistency.
How so?
Let's use the classic example. You define a shape class with a method called, say, calculator area. Then you create classes for circle, square, and triangle that all inherit from shape.
So all the children, the circle and square, they get the base features automatically. The time saving is obvious there.
Right, but here is the deeper benefit. If you need to update a fundamental feature of all shapes, let's say you're changing the way internal logging works for every calculation,
Okay.
you only make that change in the base shape class. And the update instantly propagates to the hundreds of circle and square objects across your entire system.
So you aren't just saving time writing code.
Yeah.
You're drastically minimizing the debugging effort required when you have to make these big structural changes.
It promotes stability.
It's the difference between updating one master document versus updating every single copy individually.
Precisely.
Okay, so moving on to polymorphism, literally many forms. How does this concept apply that same efficiency and flexibility, but to behavior?
Polymorphism enables a single interface, or maybe a single command, to trigger different underlying implementations, depending on the specific type of object receiving that command.
Wait, hold on. If one command can do 3 different things depending on which object gets it, doesn't that make the code more confusing or harder to follow?
That's a great point.
It sounds like it kind of violates that neatness we just achieved with encapsulation.
It's a common misconception. It only gets confusing if the implementations are entirely unrelated. Polymorphism is built on the expectation of a consistent shared behavior.
Okay, give me an example.
Think of a remote control for your TV. You press the volume up button. That single interface, volume up, executes different specific physical mechanisms depending on whether the remote is controlling your TV or your soundbar or maybe your streaming device.
So the command is the same, but the object itself knows how to execute that command based on its own specific identity.
Yes.
It provides abstraction at the behavioral level.
Exactly. It lets programmers write generic code that can handle a dynamic, diverse set of objects. And if you introduce a new type of object, say a new type of speaker, the rest of your application that calls the volume up method.
You don't need to change it all.
Often no. Not as long as the new object adheres to that inherited structure.
That brings us neatly to abstraction, which is the third major pillar, and it feels deeply connected to both encapsulation and polymorphism.
It is.
The sources define abstraction as the concept of hiding complex implementation details and showing only the necessary parts.
Abstraction is fundamentally about mental economy for the developer and clarity for the user. It's the practice of creating a black box.
It's very relatable. When you drive a car, you abstract away all the complexities of the internal combustion engine.
Right.
You only need to interact with the steering wheel, the pedal, and the brake. Those are the necessary exposed parts.
And that car example perfectly illustrates the connection back to encapsulation. You need that sealed engine, the tightly bundled data and methods, encapsulation, before you can confidently decide which part to hide and which part to expose.
Which is abstraction.
Right. Encapsulation gives you a sturdy internal structure. Abstraction gives you a clean external interface.
So abstraction is the highest level concept here. It allows a programmer to focus on what an object does without having to worry about how it does it.
And that massive reduction in cognitive load is why OOP scales.
It's the ultimate tool for managing complexity.
It really is. It allows 10 different developers to work on 10 different subsystems without needing to know the million lines of code running in the background of everyone else's system.
That transitions perfectly into our next area, moving from these powerful design theories into the practical organization required for large projects. How should these classes be physically structured in a repository to enforce this clean abstraction?
The organizational structure is where theory meets reality, especially for projects using C++ Fe, which is referenced pretty heavily in the sources.
Okay.
The notes strongly advise separating class definitions and their implementations into 2 separate files.
The header file and the source.cpp file.
That's right.
Now, that separation can seem tedious. Why add the extra administrative work of 2 files when you could, potentially put everything in one?
There are 3 critical reasons, and they all enforce the principles we just discussed. First, and this is a practical one, it speeds up compilation time.
How?
Well, when you use a class in 100 different parts of your system, those 100 parts only need to see the header file, the definition, to know how to interact with the object.
They don't need to recompile the entire implementation every single time.
Exactly.
So the header file is basically the public contract. It says, here is what I am, what data I hold, and what methods I promise to perform.
It is, and that brings us to the second and third reasons. Abstraction and dependency management. By forcing the separation, the header file naturally becomes the exposed abstract interface.
And the implementation in the .cpp file contains the secret, complex, the stuff you want to hide.
Yep. This structure enforces abstraction at the file level.
It really sounds like this file structure itself is a powerful form of abstraction. You are only sharing the minimum information required for collaboration.
That's the high-level takeaway for any learner. Whether you're using .h and .cpp or, interfaces in Java, the goal is always to keep the implementation details hidden away from the parts of the system that simply need to use the object.
Let's pivot now to a specific advanced technique mentioned in the notes that leverages this structure to make code highly intuitive. Operator overloading.
Ah, yes. This is a classic OOP feature designed solely to improve the user experience of the developer.
Right.
Operator overloading allows programmers to define custom object-specific behavior for standard operators, things like the plus sign, the subtraction sign, or even stream operators like row.
But the question is, why bother? I mean, why go through the effort of redefining what a plus sign does?
Because you want the code to match the programmer's mental model.
Okay.
If you have a custom vector class in geometry, you conceptually know that adding 2 vectors should produce a third vector. You shouldn't have to write vector C equals vector dot add vector B.
That's clunky.
It is. By overloading the plus operator, you can write the cleaner, more intuitive code. Vector C of vector A plus vector B, it drastically enhances readability and maintainability.
And according to the source material, the custom behavior is defined using that specialized syntax operator symbol. The notes then clarify that this can be implemented either as a regular member function or sometimes as a friend function.
And this is a point of necessary complexity. What is a friend function, and why do we need this concept that seems to partially break the rules of encapsulation we worked so hard to establish?
It's like an intentional breach of the seal, right?
Precisely. A friend function is not a member function. It doesn't inherently belong to the class, but the class definition explicitly grants it special privileged access to the internal, private, and protected members of that class.
So we've created this tightly sealed black box encapsulation, but then we consciously put a special key in the hands of one specific external function, the friend function.
And we do that for very specific reasons, primarily related to operator overloading, especially when the operator needs to be symmetrical.
Symmetrical.
Yeah. For example, if you are overloading the plus operator for a point class, you might want to allow point A plus 5 a scalar integer, or 5 plus point A.
Oh, I see.
If you define the operator as a member function, the point object must be on the left side. A friend function, defined externally, allows for true symmetry.
And it's required when the operation involves 2 completely different objects, or in this case, when the point isn't the first operand. That makes the need for this specialized tool very clear. It's a necessary exception for design elegance.
It is.
For those who want to see this specific mechanism applied, the notes reference the Demis class points path, which includes not just the code, but also the doctus tests that verify the correctness of that custom overloaded operator behavior.
Which is great.
That's a great way to link the theory directly to verifiable code quality.
That reference is important because it shows that even in the most advanced corners of OOP, the goal is always consistency and maintainability.
We've covered a remarkable amount of ground today. We established the foundation of OOP, clarifying the class blueprint versus the object instance. We then explored encapsulation, the principle of bundling data and methods for robust protection.
And we dove into the 3 core design pillars that allow systems to scale and manage complexity.
Inheritance for structural consistency and code propagation.
Polymorphism for behavioral flexibility, and abstraction, which uses the first 2 to hide complexity and manage the programmer's mental load.
We didn't stop at theory either, detailing the organizational necessity of using separate header and source files to enforce abstraction at the file level.
That hn.cpp separation.
Right. And finally, we looked at the specialized, design-driven technique of operator overloading and the crucial rule-bending role of friend functions.
What you have now is far more than just, jargon definitions. You have the complete language for discussing modern software architecture.
So what's the takeaway?
When you approach a system, you should be able to instantly identify how the four pillars are being leveraged to promote structure, flexibility, and most importantly, maintainability.
Absolutely. So we'll leave you with one final provocative thought, building on what we've learned today.
Okay.
If abstraction is about hiding the implementation complexity and only showing the necessary parts, like an interface button, how does a highly modular class-based structure that separates definitions from implementation itself function as a powerful form of political or organizational abstraction within large engineering teams, allowing different teams to work independently without knowing the full internal details of the others?
That's a great question.
That's something for you to mull over as you continue your exploration of software architecture.